Hello everybody, and welcome back to another Algebra 2 lesson. Things are going to be a little bit different with these lessons because instead of using the student journal, we are trying to use this here notes packet. This packet can be found on Canvas in case you want to print off a copy for yourself, or speak to me and I'll be able to get you a copy. If you are using the Big Ideas journal, please make sure that you're able to write down this important information somewhere in the margins. I know the format may look a little bit different, but there is enough space to still write this information down. With that said, let's get started. So, lesson 2.2 is all about figuring out what's going on with these parabolas, identifying the major pieces of parabolas, and using those pieces to help us decide what it should look like. First things first, there's a section here at the top where it says the anatomy of a parabola. I want you to copy down this diagram here. I've got a huge coordinate axis here with a parabola going up and a parabola going upside down. Copy this in that section and we're going to talk about the characteristics of these parabolas. Hopefully you've had a chance to copy this down. So, first things first, let's talk about what causes a parabola to go right side up or upside down. Remember that when we have a parabola going right side up or upside down, what type of transformation is occurring? That transformation is a reflection in the x-axis. When it comes to reflection in the x-axis, remember that we are just making the entire thing negative. So, for instance, a great example of this would be our first problem here. Notice that we have y equals negative 2 times x minus 1 squared plus 8. First thing is, it would be extremely helpful for us to recall what vertex form is, because we talked about it before. The vertex form of a parabola is a formula that makes it extremely easy to find what the vertex should be in that parabola. And the formula goes like this. Y equals a times x minus h squared plus k. Notice here that our a value is negative 2. Anytime your a value is negative, it means that your parabola is upside down. So reflection in the axis, or x-axis, means that our a value is negative. So in this parabola, for instance, we know that our a value should be greater than 0. We know it should be positive because it's facing right side up. This one, we know it should be negative because it's facing upside down. That's the first characteristic of a parabola that we should be able to identify. Next up, I wanted to talk a little bit about what we're going to be looking for with these parabolas. With every parabola, there are 4 major characteristics that we are going to be working to identify. The 4 major characteristics that we can find on every parabola are the axis of symmetry, or, in other words, AOS, the vertex, the y-intercept, and the x-intercepts. The thing is, though, finding these different things is easier with some forms and more difficult with other forms of a parabola. What do you think the easiest thing to find in vertex form should be? Well, that's going to be our vertex. In vertex form, the vertex is going to be the easiest to find. So we start with whatever is the easiest to find in a certain form. The more information we have, the more information we can find. Well, how do we find the vertex in vertex form? We recall that the vertex can be written as h, k. The vertex of a parabola in vertex form is going to be h, k. So let's write that down. The vertex is just going to be whatever number you have in for h, whatever number you have in for h, comma, whatever number you have in for k. And just remember that h is supposed to be what comes after a minus sign. It should always be x minus your h value. So if you see x plus 7, it means your h should have been negative 7. In this case, what's our vertex? Well, our h value is 1. Remember, it's not negative 1. It's supposed to be a minus sign there. 1. And our k value is 8. So our vertex should be written out as 1, comma 8. Once we know what our vertex is, we can graph it on our graph. Our vertex is at 1, comma 8, so we go over 1 and up 8, and there we go. That's going to be our vertex. But what is the vertex? Well, if we take a look at a parabola, the vertex is going to be the place where a parabola changes direction. Changes direction. In other words, notice how here, if we're going from left to right on these parabolas, here we're going down on the parabola, then we reach this bottom point, and then we start going back up again. The vertex is right here, at the very bottom. When our vertex is at the bottom of a parabola, we give it a special name. It's called the minimum, because it's the lowest point on the parabola. On this parabola too, we can see our parabola goes up for a little bit, it reaches the top, and then it goes down like a roller coaster. Our vertex is the spot where it changes direction. It's right here. And this vertex, because it's at the top of the parabola, we call a maximum. You have a minimum when you have a parabola that's facing up. You have a maximum when your parabola is upside down. The next thing to find in vertex form is something called the AOS. Now, I want to explain what the AOS is first before we actually go and find it. AOS stands for axis of symmetry. Once again, the AOS is the axis of symmetry. And the axis of symmetry is basically just where we see our graph flip. Notice that both of these graphs look the same on the left side of them as on the right. So if I was to cut this graph in half, if I was to cut this parabola in half, notice how the left side of the parabola and the right side of the parabola are the exact same. We say that this line is our AOS, our axis of symmetry. Same here on this one. The line that cuts our parabola in half is called the axis of symmetry. The axis of symmetry is interesting, though, because in both of these cases, where does our axis of symmetry go through? It seems to go through our vertex. The axis of symmetry will always, always, always go straight through the middle of your vertices. So that's really important to keep in mind. Because think of it. If we know it goes through the vertex, and we know where our vertex is, it means we know where our axis of symmetry is. The axis of symmetry is always going to be written out as x equals something. So for instance, let's take a look at the one on the right here. What's the x value of our axis of symmetry? Here's x equals 0. Here's x equals 1. Our axis of symmetry is at x equals 2. We say our AOS is x equals 2, and you do have to write the x equals part. But how can we find our axis of symmetry in this case? We don't even know what our parabola looks like yet. Well, Because we know a very important piece of information, we can still find our axis of symmetry. Remember, we found that our vertex was up here at 1, 8. And remember how I said the axis of symmetry always goes through the vertex? Can't we just draw a line vertically that goes through our vertex and call that the axis of symmetry? We can. So our axis of symmetry, our AOS, is x equals, it's 1 over. So it should be x equals 1, right? But hang on a second. Our vertex had an x value of 1. What's the deal with that? The deal is your axis of symmetry is always going to be the x value of your vertex. Our AOS in this case is just going to be x equals 1, since 1 was the x value of our vertex. In other words, in vertex form, our AOS is x equals whatever our h value is, because h is the first part of our vertex. Our axis of symmetry is just whatever h is. Our h was 1, so our axis of symmetry is at 1. All right. Next up, we want to identify something called the intercepts of our graph. The intercepts of a graph are where the graph crosses certain places. Let me give you an example. This graph right here on the left, we see that our graph crosses the x-axis here and here. These points where it crosses the x-axis are called x-intercepts. And the thing about x-intercepts is they're always mirrored over the axis of symmetry. So if you can find this x-intercept, it's 2 away from our axis of symmetry. We know on the other side it should be 2 away from our axis of symmetry. X-intercepts are where it crosses the x-axis. That must mean that a y-intercept, like the one right here, our y-intercept is where it crosses the y-axis. There is something very important to note about these x-intercepts and y-intercepts. I'm going to write them over here on the side. For your x-intercepts, we may not know what the x values are, but do we know the y values of these points? We do. We may not know what the x values are, but we know that their y values are 0. The x-intercepts are where y is 0. Because think about it, if they're not moved up or down off of the x-axis, they're not up any, they're not down any, our y variable is 0. What do you think the rule about y-intercepts is? If we look at this y-intercept here, what do we know about it? Well, again, we may not know much. We may not know what our y value is, but we do know our x value. We didn't move any left or right from our coordinate grid here, from our origin. So we know that our x value is 0. We didn't move it left or right. For the x-intercepts, the y is 0. For the y-intercepts, the x is 0. It's sort of the opposite. Well, that's not going to help us with this graph, right? I mean, sure, we know that for the y-intercept that x is going to be 0, but how will that actually help us here? Well, that's just it, though. We do know that our x should be equal to 0. So, what if we, in our equation, set x equal to 0? Let's see what happens. If we can set x equal to 0 and solve, we might be able to figure out where our y-intercepts are. So in this equation, we have negative 2 times x minus 1 squared plus 8 equals y. I'm going to write this down on my separate sheet of paper. You may write it wherever you like. And we said that we want to find the y-intercept. And the y-intercept is where x equals 0. So let's just write down the whole equation again, but this time have x equaling 0. This would be y equals negative 2 times 0 minus 1 squared plus 8. Do we spot anything we can simplify here? I'm just going to draw these y's in red so we always remember what we're really looking for. Is there anything we can simplify? Well, 0 minus 1 can be simplified, right? That one's an easy one to simplify. That's just negative 1. So this is y equals negative 2 times negative 1 squared plus 8. Well, hang on a second. Now we see another thing we can simplify. We've done things in parentheses. After parentheses comes exponents, and we have an exponent. Negative 1 squared. What's negative 1 times negative 1? That's just going to give us 1. So this is negative 2 times 1 plus 8. We can keep going now. Now we see another simplification. Negative 2 times 1 is just negative 2. And what's negative 2 plus 8? It's 6. When x is 0, our y became 6. This is how we find our y-intercept. We set x equal to 0, y becomes 6, so we get the following point. We get the point 0, because x is 0, 6, because y ended up being 6. Let's graph it. Let's see what we can do. When we graph this point, we get a dot right up here. That's 0, 6. That's our y-intercept. Our y-intercept is at the point 0, 6. Okay, so we've got our y-intercept. Our y-intercept is 0, 6. Now, let's see if we can find the x-intercepts. Keep in mind, this one's going to be a little bit trickier because there's usually going to be 2 x-intercepts. Usually, not always. If we found the y-intercept by setting x equal to 0 and solving for y, how do you think we find the x-intercepts? To find the x-intercepts, we can set y equal to 0 and solve for x. This is the toughest thing to do in vertex form. In the other forms, it has varying degrees of being easy or difficult, but this is the toughest thing to do in vertex form, is finding the x-intercepts. Let's try this one out again. So to find the x-ints, we recall that the equation, once again, is y equals negative 2 times x minus 1 squared plus 8. And we're trying to find our x's. To do that, we can set our y value equal to 0 and solve. So if 0 equals negative 2 times x minus 1 squared plus 8. How do we solve this? Well, we have to remember x is in the middle of our equation. So to solve for x, our goal should be to get x by itself. This is going to require some Algebra 1 skills. How do we start to get x by itself? How do we start undoing this problem? Well, when we're undoing, we use reverse PEMDAS. So we know we want to get rid of addition and subtraction first. Let's get rid of 8 by subtracting 8 from both sides. We end up with negative 8 equals negative 2 times the quantity x minus 1 squared. What's the next thing we do for following reverse PEMDAS? Well, we got rid of addition and subtraction. we should get rid of multiplication and division. And we see that we're multiplying by negative 2. So let's divide both sides by negative 2. Negative 8 divided by negative 2 is positive 4. So 4 equals the quantity x minus 1 squared. Now this one may be a little bit of a difficult step to recall. How do we undo squaring something? What's the opposite of squaring something? Well, the opposite of squaring something is square rooting it, right? So we're going to take the square root of both sides. What's going to happen is the square and the square root cancel out, leaving us with just x minus 1. Whoops. I'll put it over here. Leaving us with just x minus 1. But hang on a second. What's the square root of 4? Be very careful with your answers, because there are two ways that we can multiply something by itself to get 4. Sure, our instincts say 2 times 2 is 4. But do you know what else times itself is 4? Negative 2 times negative 2, because two negatives make a positive. So whenever you square root a whole number, you have to remember that you get a positive and a negative answer. We got positive 2 and negative 2. You can write this in two separate equations if you would like. I'm going to write it out this way so that we can actually solve both of these. However, I also want to show you a trick that you're going to see me write it as in the future. Instead of writing it as two separate equations, we can also write it as the same equation, but with this funky symbol in front of the 2, this plus and minus sign. This means positive or negative 2. You will see it written this way. All right. Down below, we see that we want to solve for x. So this last step is easy. To get x by itself, we can just add 1 to both sides. We find that one of our answers is x equals 3, and the other answer is x equals negative 1. We found our two x-intercepts. And remember, our x-intercepts are wherever y is 0. So, we know that when y was 0, x should be either 3 or negative 1. These are x-intercepts. Let's mark this down here and take a look. If our x-intercepts are meant to be 3, 0, and negative 1, 0, we can mark these on the graph and get a really good idea of what our parabola should look like. We put 1 at 3, 0, all the way over here, and 1 at negative 1, 0. These are x-intercepts. 3, 0, and negative 1, 0. Well, now we can kind of get a good idea of what our parabola looks like. The reason why we're finding these 4 qualities is because these are what tell us what our parabola should look like. We know it's going to swoop down like this. And it's going to be the same on the other side. This is our parabola. Those are the 4 characteristics, 4 of the, let's say, features of a parabola. But there's 4 more things we're going to talk about. And these are not ways of making the parabola. These are ways of describing it. These are our descriptive sort of terms. Let's talk about the domain. The domain of a parabola is all of the x values that make it up. So it's like a list of all x values? Well, it's kind of tough to make a list of all of our x values for this parabola, right? I mean, let me zoom in a little bit and we can see. If I asked you, hey, in terms of left and right, where does this graph start? That's an interesting question because we see the furthest to the left is like at 2-ish, or sorry, -2. But this arrow shows us that it's going to keep on going to the left. It's going to keep on going left more and more and more. Does it ever stop going to the left? No, this parabola is going to keep on getting wider and wider. It's going to continue to go to the left and to the right. So it means it's also never going to stop on the right-hand side either. It seems like our domain goes on forever. This is where we have a very interesting answer. Our domain for all parabolas we're talking about in this unit is all real numbers. All real numbers. It goes through 1, 2, 3, 4, 5, 6, 7. It goes through negative 1, 2, 3, 4, 5, 6, 7. It goes to negative a billion and positive a billion. It's all real numbers. There's a symbol we use to shorten this out. This symbol, an R with a little bolded section, is the all real numbers symbol. Anytime you have a parabola, your domain is going to be all real numbers. The range, however, is a list of all y values. And we ask ourselves the same question. Does it ever stop going up or does it ever stop going down? Well, again, there's no lowest point because it goes down and down and down forever, but hang on a second. Does it ever stop going up? It seems like it does. Our range stops at the vertex. So our vertex is at the highest point here. To list off all the other possible y values would take us 1,000,000 years. So we'd like to use an inequality to show all of the y values. So here's how you set up your range. You say y, you leave a space, and you put either the highest or lowest point, your maximum or your minimum, here. Now we have to decide. Are y values bigger than 8? Are y values smaller than 8? Are y values only at 8? Where are all of our y values? What about our height? Well, if the highest it goes is 8, that means that everything less than that is a y value that works. If I gave you the y value of -3 right here, you see that our parabola goes through there. If I give you a y value of 7, you see our parabola goes through there. All of our y's here, in this case, are less than 8. But it could also be equal to 8, because 8 is the highest point we go to. So our range is that y is less than or equal to 8. Next up, we have increasing and decreasing. These are the intervals upon which we find where our graph is going up and where our graph is going down. To figure these out, we just look from left to right and see what's happening to our y values. So notice that on our left, our y values go up. As soon as it hits this axis of symmetry, though, they go back down because the vertex is where we change directions. So it seems like we're increasing to the left of our vertex and decreasing to the right of our vertex. How do we write these out? To write these out, we want to compare our x values. So notice here we have x is -1, still going up. X is 0, still going up. At x equals 1, that's where it stops going up. So we can say that our parabola is increasing every time that x is less than 1. Think about it. Here's x is 1. Here's x equals 0. we're down here. Here's x equals -1, we're here. X equals -2, we're here. We're increasing up until x equals 1. So we say, when x is less than 1, it's increasing. What's happening at 1? Well, nothing's happening at 1. That's just the top of the roller coaster. It's where our ride stops. So we wouldn't say that x is less than or equal to 1. We just say that x is less than 1 is when it's increasing. And it's decreasing afterwards. It's decreasing everywhere after x equals 1. So we say it's decreasing when x is greater than 1. These features are core to a parabola. When we analyze a parabola, these 8 things are what we're looking for. 4 things that help us construct the parabola, 4 things that help us describe the parabola. You'll see that this is going to be the same across all forms, including standard form, our next one. Standard form is interesting. You've learned about it in Algebra 1, but it looks weird. Standard form looks like this. A times x squared plus b times x plus c. Note here, because this is very important, please note that we have an a value again. So once again, just like before, that a value is what tells us whether it's right side up like a cup, or upside down like a frown. If a is less than 0, it's down like a frown. If a is greater than 0, it's up like a cup. But hang on a second, what's our a value here? We don't have one, do we? Well, we actually do. Remember, everybody, that when you don't have something in for a variable, you can use a placeholder for it. So what times x squared would be just x squared? It's 1. Our a value is 1. So we know that it's going to be facing up like a cup. In standard form, there is one thing that is much easier to find than the others. That is, oddly enough, the y-intercept. In standard form, A controls our stretch, our shrink, and our flip. This b value changes our graph in very unpredictable ways. We don't really say that our b value represents one change. It just shifts our graph and changes it in a lot of ways at once. You could think of it as a combination of our h and k values almost. But it's not one-to-one. Like if you see a -6 here, it doesn't mean you move left 6 or up 6 or down 6. It just means that our graph moves or shifts a total of 6. Whether that's up, down, left, or right, we don't know. The interesting thing is this 5 here. This 5 is our c value. It's this one right here. And the thing about our c value is, it is going to be equal to the y part of our y-intercept. Remember that our y-intercept is when x is 0, but whatever your c value is will be the second part of that y-intercept. So here, we know that our y-intercept should be 0, comma, our c is 5, so it should be 0, comma 5. This is our y-intercept here. Just like that. We can put our y-intercept now up on our graph. The easiest thing to find in standard form is the y-intercept. Standard form is nice, but a lot of things are a little bit trickier to find in it. Specifically, the vertex and the axis of symmetry. Let's start with the AOS. Unfortunately, while things tend to make sense with the axis symmetry in vertex form or vertex and vertex form, it doesn't make so much sense in standard form. In fact, it makes so little sense that we want to use a formula that we're going to eventually talk about why it is the way it is. But the formula for the axis of symmetry is that x is equal to negative b. So the negative version of whatever our b value is, or the opposite of whatever our b value is, over 2 times a. Ugh, it's a weird formula. But it is really useful. Let's take a look at our parabola again. Our parabola, the equation is y equals x squared minus 6x plus 5. To find our AOS, we say that for the axis of symmetry, x is equal to negative b over 2a. So it's going to be negative something over 2 times something. Well, what's our b value here? It looks like our b value here is negative 6. So this should be negative 6. What about our a value? Well, I mentioned before that when we don't have a number next to our x, our x squared, our a value should be 1. So this is negative 6 divided by 2 times 1. What is negative 6? Negative 6 is just positive 6. And what's 2 times 1? Well, that's an easy one. That's just 2. What is 6 divided by 2? It's 3. Our axis of symmetry is x equals 3. And remember, the axis of symmetry is really, really important because it tells us how our parabola is going to flip over. So if we know that our axis of symmetry is here at x equals 3, and we know our y-intercept is here, we know there's eventually going to be another point here. Kind of neat, right? Let me just write these down. That our axis of symmetry is x equals 3, that our y-intercept is going to be at 0, 5, and let's write down that our axis of symmetry, or AOS, is x equals 3. Well, hang on a second. If our axis of symmetry is x equals 3, what else do we know? Remember our rule from last time, everyone. The axis of symmetry is just the first part of our vertex. So it works the other way around as well. The first part of our vertex should just be our axis of symmetry. If our axis of symmetry starts at 3, it means that our vertex should start at 3. This is really crucial because now we can do some math to actually solve for the vertex. Again, we're going to have to plug some stuff in. We start by remembering that our formula, or equation for the parabola, is this. If we know that our vertex starts at x equals 3 and we're trying to find the y value of our vertex, can't we just set all of our x's equal to 3? I think we can. So, instead of x squared, this can be 3 squared. And instead of minus 6x, this can be minus 6 times 3. And instead of plus 5, well, that's going to stay the same. That's just going to be plus 5. Can we solve this for y? I think that we can solve this for y. So, let's take a look. 3 squared, we know, is just going to be 9, right? So this is just y equals 9 minus, what's 6 times 3? 6 times 3 gives us 18, or with this minus sign, it'll be negative 18. So 9 minus 18 plus 5. And of course, 9 minus 18 is negative 9, plus 5 gives us negative 4. So we plugged in 3, we got out negative 4. That means that our vertex is at 3, negative 4. Anytime you know one coordinate of your vertex, you can find the other by plugging it in. we know now that our vertex is at 3, -4. So our vertex is going to be right around here. Bam. Just like that. Next up, the x-intercepts. And this part is the toughest part to find in standard form. However, the good news is we solve it the same way we solved the last one. Before we do, I want to write down a couple of things. First off, like we said, the vertex, we just plug in the AOS for x. How did we find the x-intercepts last time? Last time, we just set y equal to 0 and solve for x. Believe it or not, it's the same thing. We set y equal to 0 and solve for x. Set y equal to 0 and solve for x. So if we take a look at our equation once again, we have y equals x squared minus 6x plus 5. If we set y equal to 0, we end up with 0 equals x squared minus 6x plus 5. However, in this case, it's a little bit tougher to find what x should be, because we have an x squared and we also have an x right next to it. This cannot actually be solved unless we remember how to do something called factoring. Factoring is the process by which we try to turn a trinomial or a binomial or a polynomial into its component parts. You may not remember this process of factoring from Algebra 1, but don't worry, we're going to talk about it at the end of this unit as well. For the moment, I want to remind you how we factor a trinomial that doesn't have an a value. To factor a trinomial that doesn't have an a value, our first step is to find something that multiplies to make the last number and adds to make the middle number. So we're trying to find a number, or two numbers that multiply to make 5 and add to make -6. Those two numbers in this case are -2. Oops, sorry, I messed that up. Our two numbers are -5 and -1. -5 times -1 is +5. -5 plus -1 is -6. So when we factor our trinomial, we get x minus 5 times x minus 1. And if we don't remember this from Algebra 1, again, don't worry, we're going to talk about this later on in the unit, and the only thing we're really using it for right now is finding the x-intercept in standard form. Well, if 0 equals x minus 5 times x minus 1, we know something interesting here. There's a rule we can follow. Let's pretend for a second that instead of these complicated terms, we said that 0 equals a times b. Do we know anything about a or b? Well, we know that either a equals 0 or b equals 0, right? If, let's say, a is 0 and b is 7, 0 times 7 is 0. So that would make it work. We could also make it work if b is 0. Let's pretend that a is 7. 7 times 0 is 0. So, just like that, we know that in this case, either x minus 5 equals 0, or x minus 1 must equal 0. And it turns out both of these can be solved. What minus 5 equals 0? Well, 5. 5 minus 5 is 0. And what minus 1 equals 0? 1. 1 minus 1 is 0. These are our two x-intercepts. Our two x-intercepts are 5, 0 and 1, 0. Let's see if that makes sense in the grand scheme of things. If we take a look at our notes once again, do these make sense? Would it make sense for us to have x-intercepts at 5, 0 and 1, 0? Why or why not? I think it absolutely does. Because remember what I said, the axis of symmetry flips our graph over. And notice how here these points are perfectly spaced apart from the axis of symmetry. So we can now make our parabola, now that we have these quantities. There we go, there's our parabola. So, once again, our x-intercepts are as follows. It's 5, 0 and 1, 0. The domain, range, increasing and decreasing are a little bit different for this one, but not so different. For instance, notice how our parabola still goes left forever and still goes right forever. Our domain is still all real numbers. That doesn't change. What about our range? Again, to find the range, we want to compare y to the maximum or minimum, the highest or lowest points. What's our lowest point or highest point here? We don't have a highest, we do have a lowest or a minimum at -4. And notice how all of our y values are above -4. There's some at -3, -2, -1, 0, 1, 2, 3, 4, 5. So we say that y is greater than or equal to -4. As we go from left to right, we see that we start off by decreasing and end up increasing. So we say that we're actually decreasing up until our vertex and increasing afterwards. So we're increasing after our vertex or after the axis of symmetry. The axis of symmetry is at 3. So we say that we're increasing when x is greater than 3 and decreasing when x is less than 3. Very nice. We've got one last form. This one's my personal favorite. Intercept form. What do you think is the easiest thing to find in intercept form? If you said the intercepts, you would be correct. The intercepts are the easiest things to find in intercept form. Let's talk about how we do that. So on a separate sheet of paper, I'm going to write down our equation once again. And we might actually already know how to do this because we did it for the last problem. So, once again, what do we know about the x-intercepts? Since the x-intercepts are where y equals 0, we can say that to solve for the x-intercepts, we once again set y equal to 0 and solve for x. So once again, we're just going to set y equal to 0 and try and figure out what x should be. 0 equals negative x plus 8 times x plus 2. But hang on a second, didn't we just talk about a situation just like this? The rule is when you have two quantities multiplying together and they make 0, either x plus 8 equals 0 or x plus 2 equals 0. So either x plus 8 equals 0 or x plus 2 equals 0. So once again, we just have to solve for x here. What plus 8 equals 0? Well, to figure that out, we can subtract 8 from both sides, giving us x equals negative 8. If x plus 2 equals 0, we can subtract, whoops, not add, sorry. We can subtract 2 from both sides, giving us x equals negative 2. Our x-intercepts are negative 8 and negative 2. That's why we use intercept forms, because it's the easiest to find the x-intercepts in. But there are some things that are a little bit trickier to find. So first off, we said that our x-intercepts are negative 8 and negative 2. So let's mark those down in our graph. Negative 8 is all the way over here. Negative 2 is right here. These are x-intercepts. Oops, I just realized I messed up. I put that at 7, not at 8. I was like, that doesn't look right. There we go. I'll just put an X through there to show that that was an incorrect point. So, the next easiest thing to find in intercept form is the y-intercept. And to find the y-intercept, what do we do? Well, to find the x-intercept, we set y equal to 0. To find the y-intercept, we set x equal to 0. And solve for y. So, once again, we're starting off with our base equation here. Y equals negative x plus 8, quantity x plus 2. And now we want to solve for y, meaning we should set our x is equal to 0. So we get 0 plus 8 in these parentheses, and 0 plus 2 in these ones. This can be simplified really easily. I mean, what's 0 plus 8? It's just going to give us 8, right? And what's 0 plus 2? It's just going to give us 2. So our y-intercept should be negative 8 times 2, which is negative 16. Our y-intercept is at 0, negative 16. Of course, our graph is a little bit too small to put it on. You could rescale your graph so that you could fit it. I'm going to choose to just envision where it goes for these notes. We know for a fact, whoops, that should be a negative 16. We know for a fact that our y-intercept is all the way down here. So that gives a little hint about what our parabola might look like. Now, the toughest things to find in this form are the AOS and the vertex. Just like standard form, there's actually a formula to find the axis of symmetry. Before we can use that formula, though, let's talk about what intercept form should look like normally. Intercept form goes y equals some number a, there's that a value again, times x minus p times x minus q, where p and q are our intercepts. Well, remember what we said about the axis of symmetry. Up here we determined, hey, if we found one x-intercept, we could find the other one because the axis of symmetry is halfway between them. You may already be able to tell where the axis of symmetry is based on the graph here because it's halfway between our points. So just graphically you can say, oh, our axis of symmetry is right here because it splits the distance between our points in half. But I want to show you how to do it mathematically as well. To find the axis of symmetry, x equals, meaning our axis of symmetry equals, p plus q over 2. We just add together our two x-intercepts and divide by 2. Remember, however, that p and q are what come after the minus sign in parentheses. If there's a plus sign like we have here, we know that our x-intercepts were negative, right? We knew it was negative 8 and negative 2. Negative 8 is our p, negative q is our, negative 2 is our q. So our axis of symmetry is just x equals p plus q over 2. Our p was negative 8, our q was negative 2, and we divide it by 2. Well, negative 8 minus 2 is negative 10 over 2. And what is negative 10 over 2? It's negative 5. Our axis of symmetry is at x equals negative 5. And does that match up with what we said? 1, 2, 3, 4, 5. It does. Our AOS is at x equals negative 5. Perfect. So then the last thing we need to find is the vertex. And again, we can use a trick that we learned last time to help us out. If we know where the axis of symmetry is, do we know where our vertex is? Sort of. We know that our vertex is going to have the same x value as our AOS. So our vertex is also going to be at negative 5 something. How do we figure out the y value when we know the x value? To find the y value when we know the x value, we just plug in to the equation. So if we have y equals negative x plus 8 times x plus 2, we know that we're plugging negative 5 in for x. So to find the y value of our vertex, we're just changing our x's to negative 5s. This is negative 5 plus 8. And this is negative 5 plus 2. Well, this is why I like intercept form so much, because the math here is just addition and subtraction. What's negative 5 plus 8? It's positive 3. What's negative 5 plus 2? It's negative 3. What's negative 3 times negative 3? We get a value of 9. So our vertex is at negative 5, comma 9. If we take a look and we try to put our vertex at negative 5, 9, let's see if it makes sense. Our AOS is at negative 5. Our vertex is all the way up here at 9. This gives us a parabola, like so. There we go. Once again, we can ask about the domain, the range, when it's increasing and decreasing. So what's the domain of this parabola? Once again, it goes on forever, left and right. Our domain for this unit is always going to be all real numbers, because our parabolas don't ever stop going left or right. What's our range? Well, the range is comparing y to either the highest or lowest point. Do we have a highest or lowest point here? We do. It's our vertex. And our vertex is all the way up at y equals 9. When we look at the rest of the parabola, is our parabola above y equals 9, or are we below y equals 9? It's below. So y is less than or equal to 9. Finally, we try to figure out when it's increasing and decreasing. It seems like it's increasing on the right since it's going from down to up, and decreasing on the left, or sorry, it's increasing on the left because it's going from down to up. It's decreasing on the right since it's going from up to down. Where does it stop increasing or decreasing? It's at our vertex, at negative 5. So now I just need to put the right signs in between. It seems to be increasing at negative 10, negative 9, negative 8, negative 7, negative 6. Those are all less than negative 5. And it's increasing as we go to negative 4, negative 3, negative 2, negative 1, 0. Those are all greater than negative 5. So there we go. Everybody, I would like us to flip the page over so we can talk about this final bit here. This page is a graphic organizer that we can use to help us with the differences between these ideas. So, let's get started. Up here, we're talking about something called parameters. A parameter is just a way of defining something. It's a way of defining something mathematically. We know a couple of interesting parameters here. For instance, in standard form, the version where there's no parentheses, we know that when our a is greater than 0, our parabola is facing up like a cup. And when our parabola is less than 0, it's facing down like a frown. That's the same for all of these. For all of these, your a value determines whether we're up like a cup or down like a frown. However, there are some different parameters for some of these. For instance, in standard form, the y-intercept is pretty easy to find. It's just the letter C. So that last number in standard form is going to be the y-intercept. In vertex form, what's the easiest thing to find? The vertex. The vertex is the easiest thing to find in vertex form. And we know that our vertex, if you look at these letters up here, the h value tells us our x, and the k value tells us our y. Finally, what's the easiest thing to find in intercept form? It's the x-intercepts. And the x-intercepts follow something else. We know that it's always going to have a y value of 0 because that's what it means to be an x-intercept. But the x-intercepts are your p value and your q value, the ones that come after the minuses. Each form has certain perks to it. For instance, in standard form, you can see the y-intercept because it's the last number. You can see the orientation because the a value tells you whether it's up like a cup or down like a frown. And it's already expanded. So it's relatively easy to do math with. You don't need to worry about parentheses. In vertex form, you can see the vertex. It's your h and k. You can see the orientation as well because the a value tells you whether it's up like a cup or down like a frown. Finally, it's easy to solve for the x-intercepts since we just turn this into 0 and simplify. In intercept form, the benefit is you can see the x-intercepts because they're your p and q values after the minuses. And once again, you can see the orientation. Finding the vertex is a little bit different for all of these. I'm going to start with the vertex form since that one's the easiest. In vertex form, the vertex is just your h value, comma, your k value. That's just your vertex, h, comma, k. However, it's a little bit more difficult in the other forms. For instance, the AOS is what you have to start off with in this one. In this one, your AOS is x equals negative b over 2a. That's how you find your axis of symmetry in standard form, remember? So to find the vertex, we plug in AOS for x and solve for y. In intercept form, it's also relatively tricky because we have a different formula. The formula for our axis of symmetry is x equals p plus q over 2. So to solve for the vertex, once again, we plug that in for x and solve for y. What about the y-intercept? Well, for the y-intercept, standard form is the easiest because it's just our c value. The point will be 0, comma, whatever your c value is. That's the benefit of standard form. In vertex form, to solve for the y-intercept, we have to set x equal to 0 and solve, meaning get y equals a times 0 minus h squared plus k, which we know 0 minus h is just negative h. But hang on, what's negative h squared? So once again, if we have something like this, what's negative h times negative h? It's just h squared. So the y-intercept is whatever a times h squared plus k is. You have to solve to figure it out, though. Finally, in intercept form, if we set our x's equal to 0, we've got two of them, remember? We want our first 0, or our first x to be 0, so 0 minus p times 0 minus q. Well, we know that 0 minus p is just negative p. 0 minus q is just negative q. So what's a times negative p times negative q? It's just a, p, q, because the two negatives cancel out. All you need to do is set x equal to 0 and solve for these. Now, to find the x-intercepts, which form is the best for it? Which form is the most well-adapted to find the x-intercepts? It's intercept form, because your x-intercepts are literally just p and q, right? So you would get the points p comma 0 and q comma 0. Those are your x-intercepts. You can find them just on site. Now, how do we find them in the other ones? Well, in standard form, we want to set y equal to 0 and solve. So 0 equals ax squared plus bx plus c, and we're just solving for x. The strategy we'll need to use for this is called factoring. This is the one that we're going to talk about again at the end of the unit for those who don't remember. But what about vertex form? When we set y equal to 0 in vertex form, how do we solve? How do we solve for x? Well, we undid the problem. We got the k to the other side, we divided by a, we square rooted it, we added the h. In other words, we're just using reverse PEMDAS. Last but not least, we want to talk about these qualities: the domain, the range, how to find the minimum and maximum. To find the minimum and maximum, it's the same for all three. We look at a value and the vertex. We should call it the a value. We look at the a value and the vertex. When a is greater than 0, remember, our parabola is facing up like a cup. That means our vertex down at the bottom is a minimum. That's where your vertex is. When a is less than 0, our parabola is down like a frown, and our vertex at the top. We call that a maximum. For the domain, it's also the same for all three. The domain is going to be all real numbers since it never stops going to the left and the right. And once again, we use this symbol to represent all real numbers. Last but not least, we have our range. While the range does depend on your orientation, it's still the same for all three. For instance, when our a is less than 0 and our parabola is down like a frown, let's pretend that this is our vertex up here. We'll call it h comma k. Your range is just going to be y is less than or equal to whatever that k value is, whatever the y of our vertex is. When a is bigger than 0 and our parabola is up like a cup, again, we pretend our vertex is at h comma k. We say that our y values are all bigger than or equal to k. That is how we take care of these three forms. My recommendations for this are as follows. Try the graphs on the next page. To sketch the graph, remember we're finding, once again, the vertex, the axis of symmetry, the y-intercepts, the x-intercepts, domain, range, increasing and decreasing. Try these out for yourself, and come talk to me if you have any questions. Otherwise, have a fantastic rest of your day, everybody.